Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 2.5, Derivative Rules. We'll start by just listing the basic derivative rules, and they pretty much say everything you might expect. The first rule we mentioned in the previous video, this is called the constant rule. It says if I take the derivative of k, any constant value, I'm going to get 0. Example. If I have the function y equals 3, that's a constant function. If I were to take the derivative of it, I should get 0. And that should make sense. What is a constant function? Y equals 3, that's a horizontal line. When I take a derivative, I'm trying to find the slope. What's the slope of a horizontal line? It's 0. So finding a derivative of a constant being 0, that should be what we expect. Our second basic derivative rule is what we call the constant multiple rule. And this just says that if you take the derivative of a constant times a function, you can pretty much ignore the constant, leave it out front, and just multiply it by the derivative of the function. Right. In practice, this is pretty simple. If I have the function y equals 5, let's say x to the third, when I want to take the derivative of this, I can ignore the 5, just letting it sit there, and then take the derivative of x cubed with the power rule that we discussed in our previous video. We multiply by the power of 3, then subtract 1 from the power, so we should get 3x squared. Ultimately, you can clean this up just by multiplying by 5, and we get 15x squared. Lots of people will skip that middle step and just say 3 times 5 is 15, and reduce 1 from the power, and get 15x squared. Our last basic derivative rule is what I call the sum and difference rule. Now this essentially just says, if I've got a function that is really the sum or difference of two functions and I want to take the derivative of it, well, I can separate it out and just take the derivative of the first function plus or minus the derivative of the second function. So really, addition and subtraction doesn't affect our ability to take derivatives. We just take each term and differentiate it independently of the other terms. Let's take a look at a few examples that illustrate everything that we can handle with these new derivative rules. All right, so directions, let's find y prime, or the derivative. All right, first example, y equals 4x squared minus 5x to the 7th plus 3. To take our derivative, we'll take the derivative of the first term, the 4x squared. Here we can utilize the power rule, but also that constant multiple rule where the 4 just sits there. We'll multiply by the power of 2, giving us 8, and reduce the power by 1, so that should give us 8x to the first. The addition and subtraction rule allows us to skip over to the next term and take the derivative of that. That'll be, again, a power rule and constant multiple rule. Multiplying by 7 and reducing the power by 1, we have minus 35x to the 6th. And lastly, we run into this plus 3 term, and the derivative of a constant, which 3 is just a constant, there's no variables there. Derivative of any constant should be 0, so it should be plus 0 at the end. We can obviously clean this up to just write 8x minus 35x to the 6th, and that would be our derivative. All right, let's make our next example a little bit harder. Let's say y equals 3 over x squared minus the 5th root of x to the 7th. Here we can't apply the power rule yet because our function isn't written as terms with x to a power. So we're going to have to change what our terms look like, rewriting them. First term we can write with a negative exponent, 3x to the negative 2nd. Second term we can convert to a rational exponent as x to the 7/5. Now that I've got x to a power, we can apply the power rule, and our first term we will multiply by the power of negative 2, giving us negative 6, reducing the power by 1, x to the negative 3. We jump to the next term, differentiate with the power rule, we multiply by 7/5 and subtract 1 from the exponent. 7/5 minus 1 would get us 2/5, and there's our derivative. As easy as that. Hopefully you can see that all we're really using is the power rule. All the basic derivative rules that we learned on the first slide, they're just allowing me to use the power rule in a wider variety of instances. That being said, let's take a look at one last example. Y equals 3x cubed minus 4x plus 1 all divided by x squared. Right? Be careful not to jump in and start using the power rule. We need to simplify this first to make sure it's only x to a power. We can't have any division. So to start off, I'm going to have to divide every term by x squared. So we can split it up into all of the terms in the numerator divided by x squared. Rewriting that, that would be 3x cubed over x squared minus 4x over x squared plus 1 over x squared. Again, I can't quite do the power rule until I simplify all of these. That'd be 3x minus 4 over x plus 1 over x squared. Continuing to manipulate this function into x to different powers, that'd be 3x minus 4x to the negative first plus x to the negative second. Now finally, we can apply the power rule and take its derivative. The first term is 3x to the first, so multiplying by 1 would just give us 3. X to the 0 power, so the x is gone. Next term, plus 4, x to the negative second. And the last term, multiply by negative 2, subtract 1 from the exponent, we get negative 2x to the negative 3. And there you have it. 3 pretty diverse examples of utilizing only the power rule to handle taking derivatives of any function where the terms can be rewritten as x to a power. Make sure to check out our next few videos that describe all the ways to expand our ability to take derivatives of even more complicated functions. The next one on the product rule should be popping up right about now. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.